ahead and get started. So today we have Konstantin Batygin from Caltech, who's going to talk to us about giant planets and their spin and accretion and angular momentum and all that exciting stuff. I guess I should say a little bit about his background. So he did his undergraduate work at UC Santa Cruz before moving to Caltech for a PhD, and then to Nuys to work with Morbidelli as a postdoc, and then after that back to Caltech for assistant professorship, which he's been there for now 4 years. 4 years. What? And the CIA. Wait, CIA?
And CIA. But they teach me to hide accent. Okay.
Exactly. All right, take it away.
All right. Well, thanks so much, you guys, for inviting me out. It's a real pleasure. I decided to do something a little bit different today and not give my usual Planet 9 talk, because I found myself usually, like by now, when I give it, I just think about other stuff. So today I'm going to instead talk about some other research that I've been excited about. But whenever I try to kind of talk about stuff other than Planet 9, I usually immediately get a question along the lines of like, whoa, it's like, slow down, bro. Like, why are you trying to change the subject, right? So before we talk about Jupiter, I'd like to give you guys just a quick update on the status of Planet 9. The short story is, found it, but not telling you where it is. No, haven't found it. But here's what the data set looks like today. So this is, if we go out to the distant solar system and look at it from the top, you'll see this collection of orbits. The different colors here indicate the dynamical stability of the objects as evaluated today. So that dynamical stability, wherein the purple curves are the objects that just never do anything interesting, just slowly process around, process in their longitude of perihelion, are shown in purple. The objects which experience a little bit of diffusion, but on timescales comparable to the age of the solar system, are shown in gray. And finally, the objects that are effectively violently dynamically unstable are shown in green. So looking at this plot, you should perhaps think of the green objects, which are experiencing strong enough interactions with Neptune to be destabilized and zipped around on sort of timescales much smaller than a billion years, as effectively Nuys. The signal is coming from the objects that aren't currently being affected by Neptune. And you don't have to be at all an expert in anything solar system to kind of notice that there's a bunch of stable orbits that are all pointing this way, and there's one that's swinging out in almost exactly the opposite direction. So this is the top-down view. What about their tilts, their angular momentum vectors? Here's a projection of their orbital poles. And again, you can, I think, without too much difficulty, see that the overall all tilted in kind of the same direction with a longitude of ascending node about 90 degrees. Okay? So this is one way to look at the data. The completely equivalent but better way to look at it is in phase space. Phase space provides you with a way to work within basically an orthonormal basis set, so that you never have to worry about your variables doing anything strange. And the particular variables that I enjoy using are the so-called Poincare action angle variables. Here's the same data, only now shown in these somewhat more strange, more abstract, but nevertheless equivalent way. Here on this plot, an E equals 0 circular orbit lives at the origin, and an E equals 1 orbit lives on the circle. And the angle here, it just tells you what your longitude of perihelion is, where your orbit is pointing, okay, with some offset that I made up. And the eccentricity here telescopes in a somewhat nonlinear way, but if you're kind of close to the origin, it kind of goes as E squared. Okay, so you can really think of this as a measure of the eccentricity. And we can do the same thing for the orbital inclination and the ascending node. Okay? So the data set really is not too different from what it was a couple years ago when we first started on this Planet 9 journey. But what is different is that 2 years ago, just kind of tried my best, okay, and then just also used the computer and did some n-body simulations and found that you can sort of reproduce what we see, this clustering of the data points that is shown in orange if you put in a Planet 9 and reported what we saw. But my graduate advisor, Dave Stevenson, used to always tell me that if you can't solve the problem on the board, then that just means you can't solve the problem. Like you don't have an understanding. So something that has been bothering me for a while is how do we understand the fact that there's this clustering on this side of this plot, this side of this plot, which is nothing other than just like all the orbits are pointing one way, all the orbits are tilted in the same direction. How do I understand that without resorting to the computer? If it was 1846, how would we solve this problem? And I'm not going to go into the details of how to find these integrable models, but the short story is that found some integrable approximations which more or less explain what's going on. So here, what you can do is think of Planet 9 rather than being a planet that is perturbing particles in an n-body sense. You can think of Planet 9 as, in a phase average sense, as being a ring of mass, which is eccentric. And when you make this secular approximation, if you restrict yourself to a common plane as the Kuiper belt objects, so think of the solar system in this 2D way, what you will derive is this Hamiltonian that governs the dynamics. And here it is projected, it's level curves projected into this phase space. So what's really going on is that over long periods of time, if Planet 9 exists, the particles follow these contours, these equivalent energy contours. So that's why I think they're all clustered. They're all sitting on this hill. And importantly, over here, so this Hamiltonian, this picture, by the way, is exactly what you would get if you plotted a pendulum in the right variables. So you should think of libration of these trajectories as just a periodic oscillation of a pendulum. Okay, the directions of the orbits are oscillating, and conjugate with that, their eccentricities periodically change, thereby detaching them from Neptune, reattaching them back to Neptune. And there's one special orbit here, one special trajectory, which takes you all the way around, which is like the equivalent of a zero energy curve on a pendulum. I'm having a hard time doing this right, where you kind of come up and on almost exactly stop. So if you are sitting on such an object, such an orbit, you spend most of your time here. So I think that the existence of an object which is pointing exactly the opposite direction as the primary cluster is actually maybe indicative of the fact that it's hanging around close to the equilibrium. Yes?
Do you assume in this approximation that the orbit of Planet 9 is circular? And
No.
Is that, no. So
No.
the ring approximation that you're making for its perturbation, or its...
Yeah, it's really an ellipse approximation.
It's-
Yeah, indeed. In fact, if you made a ring approximation, you would get just a whole bunch of circles. That you would get no structure. Okay. You can basically do the same type of analysis in the inclination degree of freedom, and this is a little bit more trivial. This is just a forced equilibrium. This is just saying if Planet 9's orbit is inclined, it induces precession around the plane of its inclination. And that's all. So you can kind of look at this and say, all right. So these are all circled around here. These are all sitting on. This is the analytic version of doing Planet 9. Now, despite what you read on the news on a daily basis, it is no longer 1846. Okay? It turns out it's no longer 1846. It's just true. So one of the things you can do now is we got computers, so you don't have to restrict yourself to just doing analytic calculations. And over the last 9 months, I've done this giant suite of evolutionary m-body simulations that explore the phase space properly, which is suggested by the analytic calculations. And here, what you have is just a 4 billion year evolution of the solar system. Here, planet 9 is shown in pink. Okay? The long period orbits, meaning orbits with semi-major axes greater than 250 AU, the same orbits you were just looking at, are shown in blue. And the more proximate, shorter period component of the Kuiper belt is represented with these gold orbits. So, as you can see, now no structure develops in the low orbital period part of the Kuiper belt. The Kuiper belt, the typical part of the Kuiper belt where like Pluto and all the other famous objects live, it doesn't really show any structure, but approximately 2 billion years into the lifetime of the solar system, we're starting to see exactly what the analytic theory was telling us, namely that they're orbits that oscillate like this, like a pendulum. If you track their perihelion distances, they detach and reattach back to Neptune. This is quite important because there are indeed objects like Sedna that have perihelia far beyond the orbit of Neptune. And you can do thousands of these. Okay, and
what is driving the precession of the green guys there?
So the green guys are precessing rapidly because they see the quadrupolar fields that are the usual giant planets. So Jupiter, Saturn, Uranus, and Neptune.
So that's the complete net effect of the gaseous giants.
That's right. That's right. And this is an n-body simulation. This is not. There's nothing secular about this, but you can understand the dynamics as just these guys seeing a bunch of rings of mass, so they precess. The orbits don't close.
And why is planet 9 not precessing at all?
Planet 9 is precessing. It's just very slow. Okay, so in the entire 4.5 billion year lifetime of the solar system, it's precessed by 30 degrees. Okay, so it's not much. Okay, so when we go back to this plot and say, okay, where did the numerical simulations fall? They basically do kind of what you would expect them to do from analytic ground. So here, blue points are representing what you should be able to discover in a typical kind of near ecliptic Kuiper belt survey. And as you can see, indeed, there's this giant cluster of them here where most of the objects are. It's not perfect, okay? You get some straddlers here, and there is a notable overdensity, which indeed comes from this dynamic where you slow as you go close to the separators. And here again, the dynamics is more trivial. It's just that the equilibrium is shifted over. It's a forced equilibrium. Okay, so what all of this work that I've done over the last 9 months, together with Fred Adams, Mike Brown, and Juliet Becker, has told us is that in the first paper, unfortunately, I kind of overestimated everything by a factor of 2. Okay. The best fit planet 9 is not a 10 Earth mass planet, it's a 5 Earth mass planet with a semi-major axis closer to 500 AU, maybe 450. It's a little bit uncertain. An E that is lower than 0.6, an E of 0.3 is actually the optimal eccentricity, and a slightly lower inclination. So inclination about 20 degrees. So what does this mean for finding it? For finding it, it's actually better. 5 Earth mass planet closer in is about a magnitude brighter than the previous our previous solution. So this is all going to get packaged up in this paper that I'm finishing up right now. So it'll be out shortly. Yes?
What are the orange points?
Excellent question. So the orange points, I used orange to label things that are too high inclination to be discovered in a typical ecliptic survey. Typical survey, you look at the ecliptic because you want to discover stuff, right? You don't want to look at empty space. But, as you correctly point out, there's a lot of orange points, right, that completely overlay this plot. So we're actually in the model also generating a whole distribution of high inclination bodies. And it took us a while to figure out what was going on, but last year, together with Alessandro Morbidelli, we figured out, to leading order, what's driving this dynamic. So this is the resonance in this very strange angle. Okay? If you look at it for a while, go to sleep, drink some wine, look at it for another couple days, then go to sleep again. Okay, and wake up, you will realize that what this is a longitude of perihelion for a retrograde orbit. Okay, and I should give full credit to who figured this out. It was my former graduate student, Ganji Lee, who was just like, this is what it is, and she's right. So, long story short, in these two angle and action variables, there exists another resonance which is driving that high inclination dynamic. And it was not something that we exactly expected to be found, but earlier this year, Juliet Becker found one object entrained in exactly this dynamic, which she called 2015 BP 519. Okay? So this is a high inclination body, which is, you can see how it's beginning to come out of the primary cluster, and it's going to go on this really interesting dynamic. But point is, in phase space, it's just beginning to come up this set of phase space trajectories. So to me, this is actually a really important result, because this is something that is a prediction of the Planet 9 hypothesis rather than a retrodiction. Right now, we're about 20% complete in the 1 sigma strip of our survey that we're doing with this is, by the way, Mike Brown, my partner in crime. That's me. This is the Subaru telescope. It's not the Mechagodzilla. And we're back on the scope in December. So quite excited. So that's where we are. Let's take just a few questions before we move on to the other stuff. Yes?
So if I remember your paper, I think your original papers,
Mhm.
you showed surveys that have been done with some limits by pushing up the magnitude brighter is great, but it also means that it's more likely that it would have been spotted. I'm wondering how that plays against what we've already searched.
Yeah, that's a great question. So I think the biggest set of constraints comes from the Pan-STARRS survey, which is the claimed magnitude of completion is about 22, and I think that's a fine limit to assume outside of the galactic plane. Okay? So if the limit is indeed 22nd magnitude, then the strip of the sky that we search is about this big. Okay, so that's that's about 20 perfect nights on Subaru. One issue is that if you look, the galactic plane runs right through that strip. Okay, so in the galactic plane, you have to do difference imaging and keep scanning it because you have confusion. But that's where we are. Okay, so it's about 800 square degrees. Okay.
How many nights do you have each year?
Between 0 and 4. So it's a random number between 0 and 4. We have so last year, for example, we actually had a lot of time. We had something on the order of 6. And of them, 2.5 were just beautiful. In September, we just, carved out like 15% of the survey. And the rest of the year, it was fog, ice, wind, and other stuff. So one of the disappointing things about observing, which I'm only started realizing now, right? Before I never bothered going to the telescope. Now I go to the telescope. There's nothing to do. Just nothing happens for like night after night. So here's what I did. Okay, on our observing run, I think in February, I was just bored out of my mind. Okay, so I was looking at Twitter, right? And my friend Shannon likes to post pictures of Jupiter, and this one is just beautiful. This is from Juno, like outreach camera stitched together. You can just watch the rotation, and it's completely mesmerizing. Until you realize that something was horribly wrong, okay, with Jupiter's rotation. Okay, it's way too slow. You guys see this too, right? Why do I think this is bad? Well, I teach a planet formation class, and in my planet formation class, I tell the students with great certainty and great vigor that this is how giant planets form. Okay, first you form a core, okay, and it's something like 10 to 20 Earth masses, okay, and then this core, it sits in the disk and slowly acquires a hydrostatic envelope, and this is just achieved by Kelvin-Helmholtz contraction of the envelope around it. But then the envelope eventually becomes as massive as the core itself, and that sets in a phase of runaway growth, at which point you grow up to be a giant planet really, really fast. And I showed them this plot, which I think everybody in their life shows at least 5,000 times during talks, right? This is the classic Pollack et al. Result, where you see the formation of the core, right? And then the slow accretion of the hydrostatic envelope until the envelope becomes as massive as the core, and then you enter the runaway regime. So something that I think is important to note is that this 1D picture is very deceptive, okay? And it's deceptive for the following reason, okay? You're running up in the mass very rapidly, and you grow super fast, but you don't account for the angular momentum budget of the mass that you're accreting. After all, if I grab stuff from my environment and I accrete it along with the mass, I must also accrete the angular momentum of that material, right? That's just true. Okay, there's no way to not. Okay, and what makes matters worse is that once you grow big enough, you open up a gap in the protoplanetary disk, right? This is sort of Saturn mass, and above a Saturn mass, the accretion onto the planet, right, continues through the circumplanetary disk. And in this simulation that Frédéric Massé made, you can actually see how fast it's going, right? If you focus your eyes and just believe, okay, you can see that the circumplanetary disk is going super fast. Okay, it's orbiting super, super fast. Okay, and by the way, I don't know if this is a real simulation of this or this is just a movie, but I like it anyway. Right? You can see this, right? Right. So how does it work? You can just do it on the back of an envelope and ask, okay, well, if you just start accreting mass, how much can you accrete before you stop accreting because you're rotating at breakup? And the answer is a very small fraction of a Jupiter mass. Okay? So something is wrong with our understanding of how you grow up. Okay? So to restate this in a different way, if you're naive, like me, runaway accretion should absolutely always lead to breakup rotation, right? You should come out of runaway accretion spinning as fast as you can. And what makes matters worse is that when you form at high luminosity, you're a big planet, and then you gravitationally contract. That's the same as the ballerina bringing in her hands during a jump. You spin up. So what is happening? Why are both Jupiter and Saturn rotating at 10 hours, which is something like a third of their breakup rotation? Are they outliers? So for a long time, I think we didn't know the answer to this question, but I was on a paper recently led by Marta Bryant, who was a graduate student at Caltech, did her PhD with Heather Knudsen, where she obtained a whole bunch of V Sini measurements of directly imaged planets and brown dwarfs and compiled their data into kind of a common data set. So here's the V Sini, okay? This is, or V equatorial. You can think of it as V equatorial biased by, of course, the geometry of how you're looking at the object on the sky as a function of the planet mass. So Jupiter and Saturn are here. Jupiter, turns out, is one Jupiter mass. And this is the rest of them, right? And there's, like, I don't know anything about statistics, but even I can tell that there's no trend with mass, right? There's just no trend with mass.
Is that relevant to Jupiter? Right? I mean, if you're putting brown dwarfs on there, which may have been formed by a different mechanism than the runaway growth that you got Jupiter, right? I mean, that may change around 10 Jupiter masses or something.
It might. Yeah, it might. But do you see it changing? I don't see it changing.
Well, but I don't see anything below. In other words, you're talking about Jupiter, right? But most of what you have up there are brown dwarfs.
Mm-hmm.
So I have to just look at the points below 10
Yeah.
to look for a trend.
I disagree.
Not that I see one, but I'm
Yeah.
saying you don't have much data down where you really are forming Jupiters as opposed to brown dwarfs.
That is true. And to be completely fair, I am most comfortable. My safe space is when I don't have very much data. So I see your point, but I think that it's actually important to, at this stage when we don't have very much data, right, to look at Jupiter and Saturn and be like, look, they're just rotating slow, and so are the bigger guys, right? All I'm pointing out here is that there's a near universality of slow rotation among things that are substellar. Sure, of course they're super-Jovian. That's just because we don't have access. But I bet you that when we do discover objects, they're going to fall right here. There's not going to be a peak. I bet you 100%. I bet you one small fraction of a Bitcoin. Okay. Yes, you had a question?
Yeah, I was just wondering because there's a claim in the Ignis-Snellen's measurement of the rotation rate of beta peak that there is a relation that goes down to Mars. And I was wondering if, that was kind of maybe wild speculation, but I was wondering if you have
I think it's I know the one you're referring to. When I saw that picture, just all my 3 neurons all fired at the same time. It was an amazing moment. But I think that there is not. There's basically that plot which has beta Pig, Jupiter, Saturn, Uranus, Neptune, and the terrestrial planets all on the same plot mixes in so much physics, right? Like the terrestrial planet spins, including the Earth, right, are first set by giant collision. The Earth spun down by a lot due to tidal evolution. Venus spun down by tidal evolution a lot, right? Uranus and Neptune also have had collisions. So I think it's mixing up a lot of physics. And my bet is that that's basically a coincidence that they fall on that same line. So what about age, right? Do things slow down? Turns out the answer is no. And again, of course, we're mixing lots of different planets, but lots of different planets and brown dwarfs, which are just kind of glorified planets. There's not really, if you look at a fraction of breakup velocity, the characteristic number that you would guess for this entire data set is about 0.25, 0.1, something like that. Factors of 2 will not matter at any point in this talk. Okay? So just to, again, restate it another way, statistically, okay, this is the distribution we see of rotation rate as a fraction of breakup velocity. Okay? So something is happening. The takeaway messages here is that number 1, significantly sub-breakup velocity is the rule, not the exception. Okay, Jupiter and Saturn are just outcomes of whatever physical process determines angular momentum exchange early on. And the regulation mechanism is not age dependent, which means it probably operates very, very early on. Okay? So there's a very nice parallel that could be made here with the problem of T Tauri stars. Before T Tauri stellar rotation was measured, I guess in the early 80s, it was always assumed that stars should rotate at breakup because it's the same thing. You're taking a giant cloud, collapsing it down, angular momentum gets conserved, they spin up. Instead, they rotate at periods of 5 days and few days generically. So is it the same thing that is happening in the case of planets? You would like for it to be the same mechanism, but if you just look at the problem kind of at face value, it can't be. Okay. Why? Stars are surrounded by circumstellar disks, which stretch out to infinity AU. Okay? In other words, stars have this angular momentum bath into which they keep depositing as much of their angular momentum as they want, and the disk will simply never care, right? The angular momentum budget of the disk is way bigger than that of a rapidly rotating star. In case of planets, it's exactly the opposite. The disks, circumplanetary disks, are truncated at a fraction of a Hill sphere. And you can demonstrate that even the most massive circumplanetary disk will only have about 5% of the angular momentum of the planet. So if you invoke exactly the same process, then what you will do is you will spin down the planet by 5% and throw out the disk and be done, right? So simply copying the answer, so to speak, is not.
So I don't understand why the material that matters is not just the material at the inner boundary in both cases, because that's the material that has the angular momentum that's going to be accreted onto the star.
Well, so suppose, I mean, in the end, you're right. Okay, like if we skip to the end of the talk, yes, that's the answer. Okay, right. So I can take questions. If you look at it naively, though, right? Suppose you have exactly this picture, and this, by the way, this is a beautifully thin disk. And suppose you have a star or a planet that's rotating really fast, and you slow down the rotation of the star at the expense of moving this stuff out, right? So you're
saying the maximum you can slow it down by moving the stuff from the inner edge to the outer edge of the disk is limited in this case by the Hill radius. That's your claim.
Yeah, okay. That's the good way of pointing it. Good way of saying it. Yeah. Yeah. So what turns out to be the solution? Well, in parallel with these observational developments, there have recently been computational developments as well, where people have started doing. And this is not my work, this is from a paper by Morbidelli and company from 2014, where people now do these very complicated but kind of awesome simulations where you do a hydrodynamic simulation of the nebula, right, with the planet embedded in it, so you have the gap opening, etc. And then you do simultaneously another simulation inside the Hill sphere. So you nest your grid and you resolve the dynamics of the gas that occurs both globally in the circumstellar and the circumplanetary nebula. And something that comes out right away and this is kind of independent of the approximations you make in the code, is this pattern that I think is clearly visible with the arrows. Right? This is zonally averaged flow. You see that there's a meridional wind that develops within the Hill sphere. Okay? This meridional flow basically just comes from the fact, and this is I think in units of I want to say that this is in units of Hill sphere, but I'm not 100% sure what this circle would then be. So it doesn't really matter. Okay, what we see is that we have the circumstellar nebula, okay, which is at the midplane rotationally supported, but it's not as well rotationally supported a couple scale heights up. So what happens is the disk material over here basically falls onto the planet, okay, and forms a disk, which then decretes back into the circumstellar nebula. So this slow circulation, this is happening at maybe about 0.5% of the Keplerian velocity, is telling you that material in the circumplanetary disk is actually being continuously recycled back into the nebula. Okay. This is a higher resolution simulation by the same group, this time led by Judith Zayagi, and with a different code. So here you can sort of see the planetary disk even better, and it's quite, one of the interesting things is that it's actually quite wide. It's quite a thick disk that you form in these calculations. The fact that it's so thick should tell you right away that the disk is hot. Okay? And indeed, the disk temperatures here are about 1500 Kelvin. Why are they 1500 Kelvin? Because the planet is basically 1500 Kelvin at its formation epoch. And the planet is hot simply because its luminosity is, to leading order, just gm m dot over r. Okay, if you set that equal to sigma t to the fourth times the surface area, you get 1500 Kelvin. So what is the consequence of this all? So here, this is not a plot from their simulation paper. This is just a plot from my paper where I've kind of measured along their simulation what the temperature and midplane density are. And basically within the first 5% or so, of this circum-Jovian nebula, you have a disk that's also at about 1500 Kelvin. Okay? So the inner disk temperature is set by the planetary temperature at accretion. So what happens to rarefied gas at 1500 Kelvin? What happens is the same thing that happens to it in the atmospheres of hot Jupiters. It gets thermally ionized. And this is relatively easy to calculate with just the Saha equation. And what you get is that the ionization fraction, which arises not from hydrogen and helium getting ionized, but from trace metals like potassium and sodium losing their valence electrons, you get ionization fraction about 0.1 to 1 parts per million. When you translate that into electrical conductivity, it's basically a little bit lower than salty water. So salty water is about 1 Siemens per meter. Here you've got an order of magnitude less in terms of pure conductivity. Okay? But that's not what matters. Okay? Conductivity itself is not so important. It is the magnetic Reynolds number that tells you how important magnetic effects are going to be in this circumplanetary disk. Okay? And when you plug in the numbers, turns out the magnetic Reynolds number in these disks is about infinity. Okay? And by infinity, I mean 10 to the 6, or maybe 10 to the 4. Okay? That's because magnetic Reynolds number is the Keplerian velocity, which is really fast around Jupiter, times the scale height, which is, say, 10% of the radius. Here you have the magnetic diffusivity. So basically, even though the plasma that makes up the inner regions of the circumplanetary disks is weakly conductive, because it's going around super fast, the whole disk acts as if it was a perfectly conductive object. So here's the magnetic Reynolds number as a function of the Hill sphere, and you can see that basically out to a large fraction, maybe 20% of the Hill sphere, the entire thing has magnetic Reynolds number greater than unity. Okay? So to leading order, even though this is a crappy conductor, it's going around fast enough that it acts like a perfect one. So it's like if I took the Earth's ocean and made the circulation 1,000 kilometers a second, right? Suddenly, the Earth's magnetic field is going to start to matter to the dynamics of the ocean. Okay, so this is the first step in the calculation. The second step is actually the second problem, which is you have a disk that's ready to couple to the planetary magnetic field, but how strong is the magnetic field? Here I think, well, of course, the answer is I don't know. I don't know. I wasn't there, okay, when Jupiter was forming. But we do have a nice scaling law, okay, which connects basically all astrophysical dynamos that you would ever worry about, such as the geodynamo, the Jovian dynamo, and fully convective stars, all on the same line. There have been recently work that has actually directly measured the fields of brown dwarfs, and they do fall close to here, but they're as a rule slightly above. Okay? Not quite an order of magnitude, but slightly above this curve. So if this is indeed a good approximation, which I think it is, fundamentally this is not too different from an equipartition argument that says that generally in an astrophysical dynamo, the kinetic energy of the convection, okay, is to leading order b squared over 2 mu naught. Okay, so it's like the kinetic energy of the convection and magnetic energy are comparable. So if this is the case, okay, then the young Jupiter should have had, and here I'm, by the way, making pretty conservative estimates, should have had a surface field of about 0.5 kilogauss. So not horribly different from young Titori stars, and again similar to brown dwarfs. The recent measurement done by Melody Cow and Greg Hallinan of a 13 or 12-ish mass Jupiter mass object puts its magnetic field about 2.5 kilogauss. Okay, so this is, I think, a reasonable estimate.
So for the ground north measurements, are they assuming it's a primarily dipole field, or do they have a lot of small scale structure?
Yeah, I believe that it is, they are making the assumption, so I think that it is just coming out of basically a radio measurements. So I don't think they see Zeeman splitting. So I don't think they can resolve the difference between a dipole and, say, a quadrupole. For young stars, by the way, there's an interesting break, right? For hotter young stars that are octopolar dominated, which is kind of weird. I don't think we understand that well. And anyway, pending the understanding of that, I'm going to assume that dipoles dominate because my magnets on my refrigerator are also dipoles, and that's something I can relate to. Okay, so the picture that ensues is beautifully captured in this original Keane. You guys know James Keane? Yeah. Okay. So I actually paid James Keane to draw this beautiful diagram in cryptocurrency, which is not Bitcoin. It's this one that's blowing up right now in Azerbaijan. It's going to be huge here as soon as JWST launches. So basically, it's a very similar picture that emerges as the case of the T-Tauri stars, modulo the fact that this meridional flow plays a key role in recycling the angular momentum. So the young planet couples magnetically to the disk, loses its angular momentum to the disk, meaning expels this material slightly further out. Okay, but then this flow just carries this material and dumps that angular momentum into the circumstellar nebula anyway, and the process repeats. So that's how planets get around the issue of not having enough disk. And if you ask for fiducial kind of numbers, where does this truncation radius lie? Where does the magnetic pressure reach a critical magnitude beyond which the accretionary flow simply can't get through? It's about 5 Jupiter radii. And you should keep in mind that at this early stages, the planet itself is a couple Jupiter radii. So it's only a factor of a couple greater than the planet itself. Now, okay, from here, we can just write down an angular momentum evolution equation. This has been done many, many times, okay, in T-Tauri stellar literature. For the purposes of this talk, I will just basically assume that the disk, the entire disk is magnetically connected. It doesn't matter because most of the work is done by the inner region of the disk, and this integral goes as 1 over r to the 4. The integrand goes as 1 over r to the 4, so it rapidly converges. And this pitch angle here is just a statement about is the gas rotating faster or slower than the rotation of the star, of the planet. So what happens very quickly, okay, you can set dl by dt equal to this expression. You'll find that the equation does have an equilibrium, which is that the rotation frequency quickly goes to this value, gm over twice the truncation radius. So the equilibrium, the disk-locked state, is one where you don't exactly rotate at co-rotation with the inner boundary. You rotate slightly outside of that. So it's the torques that are coming from a little bit within your co-rotation that cancel out the remainder of the disk. And there's one more piece of information that we have to account for, which is number 1, the time scale to approach equilibrium. Turns out it's painfully short, 10 to the 4 years, comparable to the formation time scale itself in the 1D calculation. But also remember that the planet itself is shrinking. Okay? The planet, once it's done accreting, right, it will undergo its own gravitational contraction. So a second kind of implicit parameter to put in here is that hiding inside the expression for the magnetic moment is the radius of the planet. Okay, so if the planet is slowly shrinking and you assume that the field on the surface doesn't change too much, right, the magnetic moment is also diminishing. So how does the evolution look? So suppose I start my planet rotating at breakup, okay, and let it go. This is just one of my fiducial calculation. Within 10 to the 4 years, right, you will very, very quickly spin down to something like 30 hours, 40 hours, some very, very slow rotation. But then as the planet itself begins to shrink, and along with it, the magnetospheric truncation radius also diminishes, that disk-locked equilibrium state slowly marches up to a slightly higher rotation rate. So if you just plug in the dumbest numbers possible for Jupiter, which you get at the end of the cycle, right, over the magnetic timescale, slow down, then over the Kelvin-Helmholtz timescale, you spin back up to something like 10 hours. Okay. So, it's one of these things where I did not want to push it too much further, for the reason that if you do the kind of simple calculation, plug in fiducial numbers, and things work out, that's when you stop. Okay? That's when you stop. And it turns out it's not very dependent on any parameters, right? You can change the mass up and down by factors of many and not really change the evolution. But I think that this particular scenario should not be believed at the detailed level. It's just meant to highlight the relevant physical processes that are at play. Okay, so this was all written up in this paper earlier from AJ. How am I doing on time? It's 4:33. Okay, all right. So I'll tell you guys one more story. Okay, which I always like to bring up a picture of Otto Struve because he's so gangsta. Right, Otto Struve in 1952. So first of all, any question? We'll do questions later about the magnetic fields. Okay. Let me just tell you about Otto Struve. Otto Struve in 1952 wrote a paper that was like 2 pages in a journal called The Observatory. I've certainly never published anything, or have ever heard of anyone else publishing anything in The Observatory. But in The Observatory, in this 2-page paper, he was like, look, we've done a great job doing spectroscopic surveys of binary stars, and the next thing we should do is look for planets around sun-like stars that have an orbital period of about 1 day, 2 days, something like that. Like the spectrographs today can only detect them if they are Jupiter mass. Okay, but why not, right? Just found stars at 1 day periods, and that was a surprise. Let's do Jupiters. Okay, and he said, but look, the other way to detect them, by the way, is with eclipse. And I kid you not, in this paper he said, right now, like we can only get about 1% photometric depth. That's kind of the signal to, that's the detection limit. So we could only probably detect them if they're inflated, okay, and if they're 1.5 Jupiter radii. But let's find them. And then he died. Okay, this is 1952, and then he died shortly after. So we know, of course, the story that it took a little bit of time for that proposal to come to fruition. But a question that has plagued the field of extrasolar planets, okay, ever since the first detection of a hot Jupiter around 51 Peg B, is exactly how did it get there? Okay, and in my mind, I have like one of those Python natural language generators. When I see a paper about a hot Jupiter, I know what the first paragraph is going to say. It's going to say, since 1995, 283 hot Jupiters have been detected. We know they can't form where they are, so they must have migrated from 5AU site Polak 1996. Okay, that's the first paragraph of every, and I've written some of those papers. I've kind of recycled some of that words. And then, by the way, eventually we'll run out of ways to stagger those words differently. Right, and usually people think of 2 different paths from which you can take self-respecting planets like Jupiter and turn them into really hot Jupiters. And one is for them to migrate through the disk. The other is for them to remain where they are, for the disk to go away, and then something bad to happen to their orbits, and then they develop these really highly eccentric orbits. This is, by the way, a picture that Greg Laughlin, my undergraduate advisor, made, and it's one of my favorite pictures ever. Okay, so this question remains ongoing. In 2016, I read a paper that my advisor Dave Stevenson wrote in 1982, where he pointed out that as long as you have a core, okay, you can just it'll become a giant planet, right? And it doesn't matter where it is, okay? And to channel it, as long as you have a core, right? It's just like it'll just become a giant planet, provided you leave it in the disk long enough. And I was super confused by this, but indeed, okay, the core accretion calculation that we all saw a little while ago from Pollack is very insensitive to the conditions of the nebula. Okay, so when people say that giant planets can't form close to their host stars, what the right interpretation of that statement, okay, dated back into 1995, is that close to the star there is not enough solid material to make a big enough core that will then grow up to be a giant planet. Okay? So circa 1995, you cannot blame planet formation theory for thinking this, because solar system was the go-to example. But today, I think we know better. In fact, we know that the most common outcome of planet formation is a few Earth mass planet that lives close to its host star. Right? Super Earths, mini Neptunes are the dominant outcome of planet formation. I think nobody can argue with the statement. Okay, it's just true. So what happens if you put a 15 Earth mass planet? And by the way, this is not only like, oh, it's the same calculation. This is the same calculation. This is the same code from Peter Bodenheimer that was used in Pollack's paper. What happens if 15 Earth mass planet, you just put it at a temperature of 1500 K gas, let it go. Well, you wait about 1 million years, it undergoes runaway accretion, you form a hot Jupiter. Okay, now so the whole story about how they have to migrate, I think has been overplayed, and it's still a issue that's been plaguing us. It's this remnant virus of planet formation theory circa 1995, okay, that is plaguing the field today. So I wrote a paper about this in 2016, but the result I want to share with you is one that's only a couple weeks old, one that my student Elizabeth Bailey figured out, like from intuition. She genuinely just figured this out from intuition. So here's how the argument goes. Suppose you want to make a giant planet close to your host star. Okay. If you count up how much material there is between 0.05 and say 0.1 AU, it's only about 30 Earth masses. It's not enough to make a giant planet. Okay? But now, suppose, of course that doesn't mean anything, because that's just a statement about the local surface density. Okay? Disks over their lifetimes accrete. Okay? So if you are a core that has managed to enter the runaway accretion regime, you actually get to see the vast majority of gaseous material flow past by you in an accretionary way and just grab it. Okay? You just get to do that. Okay? So here's the leap that we made. Okay? We thought, okay, if this is true, if planets that are starting out as cores over here and graduating to over here, okay, really do that, if they form in situ, then their final mass, you might imagine, is proportional to the m dot of the disk. Okay, this is not like, I'm not making any crazy statements, I think. It's just m dot times some uncertain time scale. But you know what else is dependent on m dot? What else is the magnetospheric boundary? So the closest radius at which you can make this is also dependent on m dot. Okay, I had the expression a few slides ago, but it goes as A goes as m dot to the minus 2/7. Okay, so if those two expressions are true, if our expression for the magnetospheric boundary, the radius, is true, and m scales with m dot, then the inner boundary of the hot Jupiter population should have a slope of 2/7. And that's a slope of 2/7 right there. Okay. And if you adopt this line as an initial condition and run the standard equations of tidal evolution forward for 5 billion years, you will note that it will overturn like so. So, I'm not going to convince you of anything, I'm just going to leave it there and stop and take any questions.
Okay, we got 3 talks for the price of 1. You can have dessert tonight.
I accept payment in that crypto from
Questions, Bill, you had a question?
Yeah, so what does the frost line have to do with all of this? Because the original argument was that you have enough mass out where there's icy bodies.
Yeah.
And so that doesn't sound like that plays a role in your
Yeah. So the frost line gives you a boost in solid surface density, which is a factor of 2. Right? And if your model needs a factor of 2 to work, you need a new model. Right? That's my viewpoint. Okay. I think that the frost line has been completely overplayed. Its importance has been overplayed because in the solar system there is indeed this beautiful divide between the giant planets further out, the terrestrial planets further in. I think if we forget about the solar system for a second, which indeed I think it's progressively turning out to be a uncommon outcome of planet formation, just planets form, have no problem forming and getting delivered close to their star. I think it's an open question, by the way, whether the super Earths and the mini Neptunes that we see migrate. Right? So there's some people have very, very strong opinions on whether they have to form further out and get brought in, or they all form exactly in situ and they're like, I'm not moving from my orbit. Right? I think it's generally a combination of the two. I'm not an anti-migration activist by any account, but I think the story of how you make 5 Earth mass planets and 10 Earth mass planets is basically independent of the frost line. That's my view.
So you're not commenting on how you got the core there, though.
Yeah.
In the sense that you're agnostic. So in principle, arguments that relied on a frost line to make cores and then pollute it and then push them inwards would still be consistent with the picture you presented?
Absolutely. So I'm not saying that the frost line can't make the core, but I think what I am saying is that the core will get close to the star on a much shorter time scale than the lifetime of the disk, right? So that's really the argument. As far as the giant planet formation point of view is concerned, most of the mass can be accreted close to the star.
Can I ask you 2 questions that are related to this? So first is a comment.
You're asking my question, so this is...
I don't really believe the statement that you made that we know that the most dominant type of planet is a super Earth at 50 days. We only know that those are extraordinarily common. You have no information about super Earths at 5 AU or Saturns, right?
I only have information about a super Earth at 500 AU. That one.
So in principle, we could have lots of super Earths at 500 AU. The data don't rule that out. So saying that the solar system is unusual, I think that's not quite a fair representation of the data.
I disagree because even though we don't know we don't know the true inherent distribution of super Earths, in fact, I actually fully believe, that super Earths are common all the way out to like 30 AU. Okay, I can say why in a second, but we do know that giant planets are rare. Giant planets, are a 10% effect around sun-like stars and non-existent to leading order around M dwarfs. So I think the solar system, if evaluated astrophysically, is Jupiter and Saturn plus test particles, right? So I think from that point of view, it really is as far as planet formation outcome is concerned, it's a rare effect.
But my real question about your model is if you're relying on the feeding of the inner region with an infinite supply of all the material accreting from the disk, how do you prevent them from becoming much larger?
Why infinite? It's finite. You run out after a while.
You have to move the whole mass of the star through the disk?
No. You never have to move the whole mass of the star. The whole mass of the planet. And that's only like 200 Earth masses.
I'm saying to make the star, all of the mass that got to the star moved through the disk at some point to 0th order.
Okay.
Right? I mean, the star formed by getting material from the disk. So if you place a core very early at, on a 3-day orbit, how do you get it to stop at a Jupiter and not 5 or 10 Jupiter masses?
Well, so I think that the answer is that by the time you undergo runaway accretion, right? You don't start and then you're just like, all right, I'm ready, right? You still have to build up the hydrostatic envelope, which is 1 million years, and that of course depends on things that I don't like opacity and so as a consequence, I think you never experience runaway accretion in that part of the solar system right away. You wait till the disk is already quite depleted.
Do we have questions from someone on the table? All right.
I was wondering if jets are another way to lose angular momentum, that the polar jets could.
Yeah. So the answer is, I thought about it and I couldn't figure it out, and so I enlisted I have two skills. It's like if something doesn't work, I can either take out a magnet and invoke a magnetic field, or I can invoke the power of Fred Adams. Okay? and Fred Adams also couldn't figure it out. So yes, but I think it's not impossible that jets play a role. That's not something I can capture in my analytic model. Okay, and that requires basically a much more complicated, much more detailed treatment. So yes, it is possible. I don't know to what extent you can actually play that game.
I was trying to get some intuition in the second talk about this decretion and how much mass. How much mass you're actually driving out along the disk, and the effects that may or may not have.
Mm-hmm.
Have you investigated whether or not that will clear the disk or inhibit moon or planet formation elsewhere?
Okay, so this is the moon formation question in particular is, I think, an excellent one. So first of all, how much mass is recycled? The answer, I think, is like a tremendous amount, because it's moving out at something like 0.5% of Keplerian velocity. Okay. And the disk you can think of as being about 10 to the minus 3 of the planetary mass. So the disk is a fraction of an Earth mass in total, but it's being recycled very fast. But so do you ever run out of material? No, because you keep replenishing it from the top. But the question of how did the Galilean satellites form is a really interesting one, because there's no way that they would form in that disk. Okay, why? Because the disk is planet is this big, disk is this big. It's sub-Keplerian at like 15%. Okay, so if you just put the satellites there, they're like, they just decay onto the planet super fast. So indeed, I think, and then the other, of course, issue is that 1500. I don't know much, but I've seen the insides of my refrigerator, and I know it's way colder than 1500 Kelvin, right? So ice melts at a temperature substantially less than 1500 Kelvin. So how do they form? I think the answer is that the Galilean satellites have to wait until the big nebula dissipates, and then that disk is allowed to cool. And so the Canop and Ward story, where they're forming the satellites out of a gas-depleted nebula, is kind of a logical next step to the big nebula going away in this picture. Right? You have to wait for the nebula to cool and to calm down. By that time, the gas fraction is very small. And they invoked the slow accretion rate of Ganymede as the constraint to why that should work out. So I think that picture is kind of surprisingly consistent.
You had one question, and just quick.
No, I think Anne asked my question.
Okay.
Okay.
All right. Well, is there two more questions? Let's thank Konstantin again.
All right. Thanks very much.